Hey guys, how's everyone doing? So this video is just going to be an extension of the last one where we talk about rate equations. So I pretty much just have everything written down here for first order and zeroth order reactions in terms of what the rate is. And remember how I said in the last video that a rate is just a slope, right? Rate is just a slope, which is dy over dx, or in this case we're using dc over dt with respect to the axis, right? So what we have here is, the rate is equal to kc for first order, the rate is equal to k for zero order, and then the half order, the respective half-lives. Okay, so what this doesn't tell us, there's one thing that we're missing when we have these two equations, right? Let me just circle them. These two equations, there is something that we're missing, right? We can kind of ignore this for now. The half-life equations aren't that important for now, but there's something that we're missing. So we have the slope, right? Okay, so let's say we're given an equation. I'll just make up a random one. Y equals 4x plus 3. So we know the slope, right? The slope of this equation, that's easy. The slope, or the rate, or, dy over dx, it can be expressed multiple ways. Dy over dx, it could be expressed multiple ways, is 4, right? What if we're only given 4 and we're not given the actual equation of the line? How do we find the equation of the line? Well, that's where integration comes in. Derivatives, deriving something, derivation, let's do derivation is fine, is taking the equation of a line and getting the slope of it, right? So we took y equals 4x plus 3 and we found the slope is equal to 4. Integration, on the other hand, is taking the slope and finding the actual equation. Okay, so let's apply that to this, to first order and zero order reactions. So we have the slope of this, right? The slope of the rate, it's all the same thing. The slope is equal to kc, and for here the slope is equal to k. Pretty simple, right? Okay, so when we integrate this value, right? When we integrate dc over dt is equal to kc, when we integrate this, we're gonna get the actual equation of the line. So we end up getting okay, so this is like a whole process, but I'm just gonna really just break it down to the nitty-gritty, and it's gonna be ct is equal to co to the 1, I mean to the negative kt, and then when we integrate, when we integrate the zero order, we get something kind of similar. Ct is equal to co minus kt. Okay, so we have this now, right? We can automatically see that this is going to be exponential. It's an exponential graph, right? And what this means is that the graph is it's not linear. That's not what it looks like. It's going to look something like curvy. It's going to look like that. And we know this is going to be linear, right? There's no E, there's no, power or anything like that. Straight up just, you have one concentration and then you have another concentration, and your minus is something else. So it's going to be a linear graph, and I'm so bad at drawing lines, and it's going to look something like this. Okay. What else does this tell us? It tells us that CO, by the way, is your starting amount. It doesn't have to be concentration. It could be amount of drug, whatever. I think Xiao, he uses concentration, so let's just stick with that. So CO is the starting amount. CT is the amount after whatever time has passed. K, we know, is the, for zero order, this is zero order, and this is first order. So K for zero order we know is the rate. T is equal time. Okay, so we know that. We know K here for first order is going to be rate constant, and T is going to be time. So E we know, we raise that to the power. E is whatever 2.303. C is starting concentration. CT is going to be the concentration after however much time elapses. And this is generally going to be a negative process. I know I drew a positive process here, but it's generally going to be negative, right? It's going to be like a decay. So this is more what it looks like, and I don't know, leave it like that. That's what it really looks like, the blue line, because it's a negative process. Okay, so that's pretty cool, right? What we did was we just took the equation, we took the slope of the line, and we integrated to find the actual equation of the line. We took the slope of zero order, which is K, and we back integrated, and we found the actual equation of the line, right? I want to say one more thing about first order. First order, this can actually be expressed as ln, use a different color. It can be expressed as ln CT is equal to ln CO minus ET. And this is going to be the same thing. It can't really be expressed as anything else. I'm just going to rewrite it. So how do we apply this equation, these equations, to problems? And that's the most important thing, right? Xiao isn't really going to test us on how to derive it, or I don't think he's really going to test us on concepts, maybe a little bit, but ultimately it's going to be math, and how can we apply these equations to problems? So let's practice a problem. Okay, so I have a problem right here. This is straight from the textbook. Dan, you can find it in the textbook. The textbook actually was really helpful for me in terms of understanding different problems. Well, like what Xiao might ask, and this is straight from there. So okay, let's read it. A problem is ineffective after it has decomposed 10%. At the time of preparation, the amount of active ingredient was 500 mg. Okay, so what this means is that the amount of the starting material, or CO, right, is 500 mg. The starting amount is 500 milligrams. Okay, after 12 months, the amount of active ingredient was 490 milligrams. Okay, so we know that CT, where T is equal to 12 months, right, is 491. And generally, CT is less than CO, because CO is your starting amount, and you decay, so obviously CO should be bigger, right, than CT. CT is your amount after some time has passed. Okay, so what should be the expiration date if degradation follows zero order kinetics? What about if this was first order kinetics? Okay, so let's take a look at what information we're given. So we're given a couple things. We know that this, we know CO, we know CT, and we also know T. Sorry, T is 12 months. And we know the product is ineffective after it has decomposed 10%. So what is this 10% referring to? It's referring to the initial concentration. So 10% of 50, if 500 milligrams is 50, right? So let me just write that 10% of 500 milligrams is equal to 50. But it's not talking about, it's not saying, okay, when the amount reaches 50 milligrams, it's inactive. No, it's saying after it has decomposed 10%. So once this 50 milligrams loses 10% of its concentration, then it's inactive. So in reality, once it hits 450 milligrams, no good. Okay, so we know that. The last thing that we know is that it's in zero order kinetics. So it's zero order kinetics. And the other thing that should automatically click in your head, we have to use this equation, the zero order equation. So let's check it out. Okay, so what are we missing really? We're missing, we have CO, check, right? We have CT, check, at 12 months. We have T, which is 12 months. So what are we missing? We're missing k? How do we find k? Well, we plug everything else in, and k should be the only value left. Okay, so let's check it out. We have 490 milligrams as CT. We have CO is 500 milligrams minus k times t, which is 12 months. Okay, so ultimately k ends up being what? K ends up being, so k ends up being 0.75, and we know it's in zero order kinetics, right? So in zero order kinetics, k is the rate. So it's how much amount changes over amount of time. So the amount we're working with is milligrams, and time is months. So the rate of decay is going to be 0.75 milligrams per month. And generally, this is a negative process. So it should be negative k. But we're just going to leave it at k for now. Okay. So now we have k, right? Now the problem wants to know. What should be the expiration date? So what should be the expiration date if degradation follows zero order kinetics? So expiration date, time, right? That's another word for time. So if we do this in the recovery, so now we just apply the same equation again. We know k is rate, and zero order rate is a constant, right? Because it's we have dx over dt, simply k. We know that from before, and it's not going to change. It's going to be a constant. So if we apply the same equation again, CO is equal to, CT is equal to CO minus KT. Let's see what we have. So what is CT? CT is pretty much when the drug expires. So we already figured it out. It becomes no good at 450 milligrams. So CT is going to be 450 milligrams, but we don't know what time is, right? We want to find that. We want to find that time. So for 50 milligrams at whatever time, CO we have is the starting amount, 500 milligrams minus K. We figured it out as 0.75 mg. Let me just move this over. 0.75 mg per month. And time, we don't know. Time is however many months. So then we end up solving for time, and time ends up being, let me just plug this in. Okay, so time ends up being around 66.7. Let's do 7 months. So that's how long it takes for 500 milligrams to decay by 10%. So then the expiration date would be 66.7 months. Okay, so let's look at this from the point of view of first order reactions. So we know the equation for first order reactions is ln is equal to ln CO minus KT. And from the past problem, we know that CT, we're gonna start with 491 milligrams. We know CO starting amount is 500 milligrams. We know that we get from 500 to 491 milligrams after 12 months, and we're missing K. So let's plug it in. We have ln of CT, so CT is what, 491 equals ln of CO. CO is what, 500 minus K, and then T is 12 months, right? And you know what? I'm going to stress units because Shao stresses units so much, so I'm going to put units in there. Ultimately, I'm going to, just pause it for a bit, and then let me see what K is. Okay, so K turns out to be 0.0015, and we know the units for first order K is going to be per hour, whereas units for K in zero order is going to be milligrams over hour, but in first order it's going to be per hour. Okay, so now we have K, and K we know is a constant, right? It's the rate constant. So, you know what's funny? The funny thing is that K is constant in first order and zero order reactions. The only thing that changes is that in first order reactions, the rate is Kx. So then the rate is ultimately influenced by what Kx is. Yeah, but K is going to be constant no matter what. Okay, so what do we do now? We use the equation again, and now we want to find how long it takes for the drug to get to 450 milligrams, right? My handwriting is so bad. All right, 450 milligrams. When does it get to that? You know, we want to know. That's what we want to know. Okay, so same thing. You know, we do ln 450 milligrams is equal to ln. Starting amount is always going to be the same. You're never going to change really your starting amount. 500 milligrams minus K we know now is 0.0015 per hour. And time we want to find out, right? So the only thing that changed is that instead of having CT as 491, we have CT as 450 now. So then T ultimately is, give me 1 second. So T came out to be 70. 70, what are the units? It should be hours, right? So the time it takes for 500 milligrams of drug to decompose 10% is going to be 70 hours, so therefore the expiration is 70 hours from when you make it. So there we go, that's the whole Shazam. Alright, good night.